for the introduction. So, okay. So I hope I am audible.
Yes,
Yes,
you.
yes, you are audible.
Yeah, thanks. So without delaying, I will start presenting my screen. So is my screen visible?
Yes, it's visible.
Yeah, thanks. So good afternoon, everyone. Today I'm going to give a talk on classification of compact surfaces. The name's been a bit more exotic, like title is a bit more exotic, and like a mathematician's dream of doing surgeries. But like we are not going to do surgeries for real. And okay, so if you are familiar with a little bit of algebraic topology, I think most of the steps will be very comfortable for you. But if you are not, I have tried to keep this very intuitive, and I hope like you guys can easily follow the talk. So, what are surfaces? If you are familiar with manifold theory, a surface is just a two manifold. Basically, it is a Hausdorff second countable space, which is locally flat. What I mean by locally flat is, so if you have your space S and you take a point P on that space, you will be able to find an open set U around it and a homeomorphism phi from the set U to R2. So this is a homeomorphism. That is basically what locally flat means. And in mathematics, like this is a general philosophy, this is what we want to do. What is our ultimate goal is we want to classify objects up to certain constraints. And in this particular case, our goal is to classify compact surfaces up to homeomorphisms. Okay. And why do we want to do this? Well, to give you a suitable reply, I would say like this is an interesting problem. And I think that is enough, like that is a good enough reason for any mathematician to look into this problem. And why is it difficult? The reason being, if you look at, so I've drawn certain examples over here. If you look at them, at this point, we don't have a very systematic way of distinguishing surfaces. Like, we don't even have a clear image, like what a surface should look like. What we will do is, first of all, we will focus only on the connected components of the surface and try to understand what they are. But even in that particular case, like if you look at these examples, there's a really weird spaces. Like if somebody had told you and woke you up in late night and told you like, see, this is a torus. At the first glance, you might be confused. Like, well, is it a torus even? But so this is the issue. The problem is we don't really have a good picture of what surfaces should look like. And the first step is like trying to understand what they will look like. Okay, and I've given a few non-examples. So like these are not surfaces, even though they look like one. The reason being, so if you recall, a surface it has to have neighborhoods which are locally Euclidean, like locally flat. But in case of the Mobius strip, if you look at points around the boundary of the Mobius strip, what happens is these don't really have sets open like neighborhoods which are locally flat. They actually have sets which are sort of what to say, uh, they look like half plane. So like there is a certain edge attached to it. Okay, so these are not similarly for the cylinder. Like if you look at over here, the boundary points, they don't have locally, they are not locally flat. So these are mm, some examples which are not surfaces, but they are actually surfaces with boundaries. But again, our talk today is like we will be focusing on just surfaces, not surfaces with boundaries. Another important fact that I will mention over here because like we will need it in our talk. So this is a very cool party trick. So you can easily construct a Mobius strip. Take a long strip and then twist the ends and then glue them. There you get a Mobius strip. So what you can do is to impress your friends who are not familiar with this trick, you take the equatorial circle on the Mobius strip and the equatorial circle on the cylinder. So for the cylinder, if you cut along the equatorial circle, like you will get two connected components. Like you will get two copies of cylinder. But in the case of Mobius strip, something interesting happens. You won't get like your paper won't disintegrate into two parts. In fact, what you will get is a long cylinder. If you know this trick, then it's really nice. If you are not familiar with it, I will suggest you can try to solve this using some ideas from quotient topology. This is not a difficult problem to solve. Okay. So coming to some ways of constructing surfaces. So in our talk, the sphere is going to be like the sphere is going to play a very pivotal role. Most of the surfaces, what we will do is we will build it from the sphere. So in the first example, what I do over here is I take the sphere, I remove two holes. So these are holes inside the sphere. So I remove two holes, which looks like disc or like which have boundaries, which look like circles. And then what I do is I glue a cylinder along these holes and get a new surface. So I glue them together. Uh, so like glue the centers together, like the circles together, and you get a new surface. And we will call this genus one orientable surface. You don't really have to worry about the orientation stuff at the moment. Just remember, like you can do this and you get a new surface. And you can do it like you can attach, so you can attach n handles and you can get something which is called uh, genus n orientable surface. Okay. I can do the same trick with a Mobius strip. What do I this time what I do is I punch only one hole and now the boundary of the Mobius strip is a long circle. What I do is I glue the boundary of the Mobius strip along the boundary of this hole and I get a new surface which I call a genus 1 non-orientable surface. Well, it is very difficult to draw it in 3 dimension because like there will be self-intersection if you try to draw it in 3 dimensions. So bear with me, this sort of a symbol on the sphere, it basically means I've attached a Mobius strip along its boundary. And once again, you can attach uh, n many Mobius strips and then you will get something called a genus and non-orientable surface. Again, like at the moment, you don't have to emphasize on the word non-orientable, but or like orientation, but we will come to it later. Okay, so what happens if we attach a Mobius strip? Sorry, if we attach a handle in presence of a Mobius strip. So I have a sphere over here. I've already attached a Mobius strip, and later I've attached a handle. How will this face look like? And this is the trick that we will follow throughout this lecture. The idea is you cut your surface and keep the identification intact. So I've cut a disc around the Mobius strip over here. So if you look at it, I've cut a disc around the Mobius strip and I get a hole over here. So this is a hole in the sphere with a handle attached to it. What I will do is I will show you that this space is actually homeomorphic. So this space is actually homeomorphic to this space. The reason being, with the hole, like in the presence of that hole, what you can do is you can take this handle and send it inside. Okay, you can do this kind of so like these things can be made rigorous, but at the moment you can sort of think homeomorphisms as just continuous deformation of your space. And once you do that, well, what is this guy? if you look at this guy, this is actually a Klein bottle with a hole punched in it. Okay, and this is another famous party trick. Like you cannot perform it practically, but another sort of a good example, you can perform it in front of your mathematician friends. What you can do is you can take two Mobius strips and attach them along their boundaries, and what you will get is a you will get a Klein bottle, and that is what this guy is. But you have to punch one more hole over here, and for that, what I do is I attach two Mobius strips on the disk, and I have a boundary that sort of justifies that these two guys are homeomorphic. And finally, what I do is I glue them back. So, like I at the first I had cut out them, and what I do now is I glue them back, and I get a space like this. So eventually, what I showed is in presence of a Mobius strip, attaching a handle is same as attaching two Mobius strips. So
So
this,
cutting and gluing back the spaces, we get a homeomorphism.
yeah. So what I did was, remember, so I did the homeomorphism along this space only. Okay, I can do it along this space also. It doesn't really matter. But what should be kept intact is the identification. You should not, like, what to say. You have to remember what happens after you do the homeomorphism. You have to remember what happens with the identification, because you have to identify the homeomorphic copy along that identification space only. Okay. Okay. I hope that clears your doubt. So what we have seen so far is uh like the attaching Mobius strips and attaching handles are sort of preliminary examples of surfaces. And okay, so just a notation over here. So when we attach G many handles on a surface, on a sphere, we will denote that space by sigma G. And when we attach G many Mobius strips on a surface, we will denote that space by Ng. And the heart of today's talk is to understand and prove this theorem, which is the classification theorem of compact surfaces. So which says that up to homeomorphism, any connected compact surface is going to, like, it's going to be one of the three types. So it is either going to be a sphere, or it is going to be a surface which is homeomorphic to sigma g, or it is something which is homeomorphic to Ng. This is the main result of today's talk. But now, as I was saying earlier, we will look at ways in which we can sort of visualize our surface. The surfaces at the moment is a very abstract object. We have to find a precise way to visualize them. And over here, what we'll do is we'll sort of set up a combinatorial structure on the surface, which will help us to study the surface. Uh, in general, you can do this for any manifold, for any dimension, like not the triangulation, but like this sort of argument on of simplices. It can be done for any dimension. But since we are focusing on, like, our focus is on surface, we will only deal with simplices which are of dimension 0, 1, and 2. So a zero simplex, as the picture shows, is just a point. A one simplex is actually a line joining two points, and the two distinct points. And what I so these 2 points over here, the two endpoints, these are actually subsimplices of a one simplex, because like these are zeros simplexes in that one simplex, and a two simplex is a triangle where the 3 points actually form a non-degenerate triangle. Okay. And once again, like, you have got subsimplices, but this time you have got more subsimplices. So you have got one subsimplex. So this is a one subsimplex. So the edges form three one subsimplices, and then you have got zero simplices, or zero subsimplices also, which are the vertices of the triangle. Okay, good. Now, what is a simplicial complex? So, what we'll do is we will patch along these triangles sort of to get a space which will look like ours, which will look like the surface we want to study. And to make these things precise, I need to make this following definition. The simplicial complex is going to be a collection of simplices. So a priori, this is just a set in of simplices which are embedded in some large Euclidean space. I don't care about the dimension of that Euclidean space. So, and what are the properties? So, whenever a simplex is it is sorry. So, whenever a simplex is in the collection, then all of its subsimplices are also there in that collection. And we need one more condition which says that whenever two simplices intersect, they do so in a good configuration, meaning that they should intersect only along subsimplices. So if you look at this example, so I've drawn an example of a simplicial complex. What I've done over here is I've taken four uh, two simplices and I've attached them along the boundaries like this to form a tetrahedron. And eventually I've also added a one simplex to one of the vertex points. This is a simplicial complex because if you look at the intersection of the subsimplices, like if you look at the intersection of any simplex, so if you look at this one simplex, it intersects only at this zero simplex. And if you look at this two simplex, like this to two simplices, they intersect only along this edge. So this is a good configuration, and this is an example of a simplicial complex. But if you look at the later example, this is not a simplicial complex. Reason being, these two simplices, they have got what to say, not a good intersection. They overlap and they are not intersecting along uh, what is it, along a subsimplice. So this is not a simplicial complex. Now I was saying that this collection of simplices, it is actually embedded in Rn, and it will automatically inherit a topology from Rn as a subspace topology. And to be precise, what we will say is like we will denote this space with the subspace topology from the Euclidean space by this notation modulus of the set K. Okay, and a surface is said to be triangulated if there exists a simplicial complex and a homeomorphism from the what to say, like the geometrification of the simplicial complex. If you have a homeomorphism like this, then you say your surface is triangulated. So just a few observations. Since we are dealing with two manifolds, as I was saying, we will be only focusing on 0, 1, and 2 simplices. And since our manifold doesn't have a boundary, so any one simplex must be a common edge of exactly two simplices. It cannot be edge of one simplex because then you get a sort of a boundary kind of a thing, which is not what we are looking for in our surface. And it cannot be a part of three or more two simplices because then locally that space is actually not R2. Okay, so let us look at,
Hello, I have a
yeah,
question. So the
yeah.
intersection of the simplices is like the set theoretical intersection where you are considering the set uh, set of the subsimplices and where the set intersects and you get the good intersection.
Yeah, so your collection consists of simplices, and by intersection, I mean just the set theoretic intersection in Rn. So it is a subset of both the simplices, and what I'm saying is that subset, it must be a subsimplice of both the simplices.
Okay, oh, got it. Thank you.
Okay, no problem. Okay, now let us look at a few examples. Okay, so a sphere. You can giving an explicit homeomorphism is a bit difficult because like you have to just draw a lot of, like you have to derive a lot of formulas, but I hope you can understand, like you can easily triangulate the sphere by forming a tetrahedron which is formed by joining four two simplices along the one simplices like this. Good enough. And the torus, if you remember from your quotient topology class, a torus can be drawn like this. You have a rectangle and you identify the opposite edges in the same direction. And I have given sort of, this is not the best triangulation possible on the torus, but it does our job. So be happy with it. And this is sorry. So this is a triangulation on the torus. Now, the key result, which we will avoid, like, we will avoid the proof of this result because like it is a very technical result, and going into the proof won't actually benefit us today. But I would suggest if you want to read the proof, you can go ahead and look at. There are lots of examples. Like you can look at Rado's notes, and there are a few more tricks, sophisticated tricks, which uses which gives a proof of this result without using what to say, the Jordan-Cook theorem. But like this is something that we will assume for today. That is, every compact surface can be triangulated. Okay, great. If we allow me to assume that, then I can say that, so I have a surface, it is homeomorphic to a triangulated surface. Now this triangulated surface is, it is actually a combinatorial object, because like I'm forming it using by attaching triangles along edges and the stuff like that. So I can talk about trees which are like uh like tree in the graph theoretic sense. Like trees are just going to be one dimensional subcomplexes which don't have any loop in them. So I can talk about, I can use some combinatorial tools now to study our surface. Okay, but before going into those, so I need to build up some tools. So this is again a philosophical, but what the idea is, so whenever you want to classify certain object, what do? You first try to simplify the simplify the object. So we have already done that using our triangulation. We have sort of simplified our object. Now you build tools on that simplified object. So, and those tools will help you to distinguish and sort of to classify the object. And one of those tools that we will use today is the Euler characteristic. So given a triangulated surface, you define the Euler characteristic as follows. So you take the number of zero simplices, then you subtract the number of one simplices, uh, and finally you add the number of two simplices. So a priori, this formula depends on the triangulation of the surface, but this is a sort of a not a very difficult result, but you need to know some machineries, which is homology theory, to show that, in fact, this doesn't depend upon the triangulation. And so I've written it over here. What happens actually is the Euler characteristic for a compact surface is actually given by this formula. So you look at the integer graded homology groups, and you look at the rank of them, and you take their alternate sum. Okay.
This
So
is reminiscent of the graph theoretic result, right?
yeah, exactly. This is a very reminiscent of the graph theoretic result. You look at the, so if you remember the graph theory formula, so it's V minus E plus F. It's exactly that thing. Okay. So let us do some computation, some trivial computation. What about the Euler characteristic of the surface of the sphere? So I have a triangulation like this. Let us count the number of vertices. So there are one, two, three, four vertices. Great. Okay. Let us now count the number of edges. So there are one, two, three, four, five, six edges. And let us now count the number of faces. So there is one, two, three, and one face below. So there are four faces. And our Euler characteristic turns out to be two. Good. And let us also, you can do it for the torus on, like there are like maybe you can do the case for the torus, and what you will get is you will get zero. uh, just do the calculation. There's nothing much over here. Okay, that being done, and we will assume that the Euler characteristic is a invariant up to homeomorphism. Okay, next up we need to discuss about barycentric subdivision. So actually, you can sort of. go ahead in this talk without talking about barycentric subdivision. But barycentric subdivision, yeah, sorry.
Uh, this the Euler characteristic that you just wrote is for two manifolds, right?
Yeah,
For
yeah,
two things.
yeah. This is for two manifolds. In general, if you have an n manifold, then you will have like you have to sum up to indices up to n.
Okay, okay, got it.
Yeah. Uh, yeah. So where I was the barycentric subdivision. So yeah, as I was saying, the barycentric subdivision you can avoid the proof without going into these details. But I think if you want to make the proof a bit more precise and rigorous, then I think one needs to talk about barycentric subdivision. So barycentric subdivision, as the name suggests, what you do is you give equal weight on each of the vertices, and then you construct the centroid of each of them. So if I do the barycenter. So what I do is, given a simplex, I first compute their barycenters. So for a zero simplex, the barycenter is going to be just that point. For a one simplex, the barycenter is going to be the midpoint of that line segment. And for a two simplex, uh, the barycenter is going to be the centroid of the triangle, right? Now suppose you have got a collection of simplices like we had in general. So let me just give this example for the particular case of a two simplex only, and we can generalize this results for any collection of such simplices. So I have a two simplex like this. Okay, I construct all the barycenters. So what are they going to be? So for each of the vertex, I will get a barycenter at first, because like the barycenter of the vertices are just the vertices itself. Now for each of the one simplex, I will get another barycenter, which is the midpoint of them. Great. And finally, for the triangle, I will get another barycenter for the two simplex. Now what I do is, I will draw a edge between the two barycenters if the simplices that they came from are actually faces of a larger simplex. So what I mean is, so let us take this barycenter and this barycenter. So this one came from the zero simplex over here, and this one, it came from the barycenter of this edge, right? And now this edge, it contains this vertices, this vertex. So the simplices that they originated from are actually faces of one another. In those scenarios, we draw an edge between them. So similarly, we have to draw an edge over here. We have to draw an edge over here. And we have to draw an edge over here, and an edge over here. And now let us look at this guy. This vertex, it came from the triangle, the two simplex, and it contains both of the vertices and this one subsimplices. So what I will do is I will join a edge between each of the barycenters coming from the zero simplex and the one simplex. And this gives us a division of the original simplex into a much more finer simplex. So like I had started with one simplex, and now I have a much more finer sort of way of finer triangulation on that one simplex. And in general, if you have a simplicial complex, you do it on the whole simplicial complex, and what you get, we call it the first barycentric subdivision of K. And if you keep on doing this, you get the second barycentric subdivision. So if you do the barycentric subdivision on the first barycentric subdivision, you get the second barycentric subdivision. And if you keep on doing it, you get the nth barycentric subdivision. Uh, in this particular talk, we will mostly focus, like, we won't need to go beyond second barycentric subdivision. So I think now we have done a lot of definitions, and we will now sort of come to what is the main lemma in the proof of classification of surfaces. So as the name suggests, what I do is Poincare type of conjunction in dimension 2. So if you remember at the start, I was saying the sphere is going to be a building block for our surfaces. So at first, we sort of need to precisely give some ways to distinguish the sphere. And the way we do is like let's look at the definitions first. Okay, so simple. So given a surface and a triangulation on it, a simple closed polygonal curve is just a curve which are formed by the one simplices of k. Okay, and we will say that the simple curve. I won't mention that simple closed polygonal curve. Sometimes I will just say simple curve. So I will say that the simple curve is separating if the this set, so the simplicial complex minus the curve has two components. Basically, if it's disconnected, okay? And we will say a surface is sphere-like if any closed curve in K separates it. Okay, great. Again, this definition once again, it seems like it looks on the triangle, like it depends on the triangulation, but like what we are will show is like it really doesn't depend upon the triangulation, and we will this lemma, the lemma 2 will help us to do that. Okay, so a sphere is sphere-like, and this is very obvious. The reason being you can give a very easy triangulation on the sphere, though the tetrahedron kind of a triangulation, and I will leave it up to you guys to just check that if you pick up any simple closed curve which is polygonal over here, so a polygonal, so it has to be along the edges, then if you it will disconnect the space. That is very obvious. Like you have to just look at some finite examples and you are done. So this is true. Okay, now the key lemma, so this is sort of the Poincare lemma. So this is sort of the Poincare conjecture. So if you know about Poincare conjectures, this is sort of what to say, a baby version of it in dimension 2. This is not even a conjecture, this is a trivial lemma. So okay, I'm saying that given a surface, the following things are equivalent. First, if if it has all the characteristics 2, then I'm saying that it is homeomorphic to S2 and S is PLI. So the proof of this lemma, we will come to it later, because like at the moment, I think we should just go ahead and so take this lemma to be true for the moment, and we will come to the proof of this lemma at the end. Okay. So just a few more constructions, and this is where we will need the second barycentric subdivision. So given a simplicial complex, and let you have a collection of one simplices, what you do is to just look at this example. So I have a simplicial complex, and I look at a collection of one simplices. So the red lines denote the space L. What I want to do is I want to thicken this space L so that I get a neighborhood around it, which is in some sense almost the same as that space L. So the word I want to use over is homotopic. So I want to find a neighborhood around L which is homotopic to L. Okay, and the way we do is you go on to the second barycentric subdivision, and then you take all those simplices which have non-empty intersection with your the starting collection of one simplices. So if you look at this diagram, I did the first barycentric subdivision, then I did the second barycentric subdivision, and then I've shaded those simplices which have non-empty intersection with the line L, with the subspace L, and this is what we will call NL. So this kind of neighborhood we will denote it by NL. Okay. Few things to observe. If L is a tree, then this neighborhood NL, it is actually homeomorphic to a disk. And the way you do is by induction. So if you had only one vertex, then of course you will get all the simplices around it and you get something which looks like a disk. Suppose it is true for any n minus 1 many vertices, then when you have one more new vertex, what you do is you first discard the end vertex and you get a n tree with n minus 1 vertices, which is homeomorphic to D2 by our induction hypothesis. And lastly, when you attach the simplices which are around the end point, you have to glue them along the edge and you will again get a disk over here. So in general, for any tree, you will get that the neighborhood NL is homeomorphic to a disk. Next up, another observation is if L is a simple closed polygonal curve in the simplicial complex, then NL is either homeomorphic to a cylinder or it is homeomorphic to a Mobius strip. The way you do is, so if you have your if you have your neighborhood around the so the NL, what you do is, since it is a simple closed curve, so say your this is sort of the rough idea. So these are formed by the vertices over here, and the eventual vertex is V0, and this is Vn, Vn minus 1. So what you do is you remove this part, then you get a tree consisting of n minus 2 vertices, which is homeomorphic to a disk by our, so for that case, the neighborhood is homeomorphic to disk from our previous observation. Finally, you have to attach the neighborhood along Vn minus 1. So there is an edge over here for Vn minus 2, and when you attach along this edge, and there is an edge over here for V0, and you have to do two identifications over here. Okay, so once you do the identification on one side, now the other side, there might be two cases. So there over here in this identification, there might be two cases. What are they? So first case, it might be you have to make a twist, and the other case is don't have to make a twist. So in the first case, if you have to give a twist, you will end up with a Mobius strip, and if you don't have to give a twist, then you will end up with a cylinder. So that is what this observation is telling you. Okay, and so whenever the neighborhood is homomorphic to a cylinder, I will call the simple closed curve to be oriented. I will say it is oriented, and if it is not the case, then I will say it is non-oriented. Okay, again another. So like, bear with me. This is, I think, the final construction that we are going to do today, and then we will go directly into the proof of the main theorem. So this is a result from graph theory. I think you know that given a graph, you can given a connected graph, you can always form a maximal tree. Okay, so this is what I do. I take a simplicial complex, and then I take a maximal tree in it. Okay, then I look at the first barycentric subdivision, and for each phase, I look at the barycenters, and what I do is I join the one simplices of the first barycentric subdivision, which are not intersecting the maximal tree. Okay, I hope this is fine. Look at the figure for reference over here. So I did the first barycentric subdivision, and I took at the barycenters, and then what I did was I joined those one simplices which have non-empty intersection with our maximal tree. So this purple curve over here, the purple graph over here is that example. Okay, and we will call this the dual graph uh, of the space of the tree. Okay, and now you define a neighborhood U gamma, and the way you do is you, since you are already in the first barycentric subdivision, you go on to the second barycentric subdivision immediately from there, and then you look at all the subsimplices, all those simplices which have non-empty intersection with your dual graph gamma. So yeah, with your dual graph gamma, and you call that to be
Dual graph missing a edge.
which one?
The one at the far end.
One at the far end. Do you mean this one?
Yeah, yeah.
See, okay. This is I have drawn that over here. I think it's not very visible. The thing is, this edge is identified with this edge, and this edge is
Okay.
identified with this edge. So actually, this vertex is
I see.
exactly same as this vertex. So that's why I have not drawn that edge.
I see.
Okay, great. So some immediate observation is this. By our just from our construction, what we have done is we have, if you look at the second barycentric subdivision, NT and U gamma, this actually contains all the sub simplices, and they are what to say, like the union of them is the whole simplicial complex. Because like if in K2, like K2, I mean the second barycentric subdivision, any simplex which misses the graph, T, it must have a non-empty intersection with the graph gamma. Okay, because like our starting graph was a maximal tree. Okay, and so for a maximal tree, this thing is true. And further, what is true is if you look at the intersection of the neighborhood around uh, T and the neighborhood around gamma, they intersect only along the boundary of NT. And recall, T is a graph, so the neighborhood NT, this is homeomorphic to homeomorphic to a disk. So the boundary is actually homeomorphic to a circle. Okay. Another observation is U gamma is path connected, and this will imply that gamma is path connected. Why is U gamma path connected? So just take any 2 points in U gamma, and now since our space is now the whole space is path connected, what you can do is, so I will just quickly draw a figure over here. So say this is the part in U gamma and this is the part in NT. This is just a rough diagram. So you take two vertices in U gamma, and now you know that our whole space K, this is path connected. So you can always find a path along K, and you draw that path. And now you take the vertices for where like the first time it crosses U gamma and goes into NT, and the last vertex where it crosses NT and comes to U gamma. And what you do is you discard this whole part and instead look at this edge, which is in U gamma. And this gives you a path in U gamma. So U gamma is path connected. And as I was saying, since gamma is homotopic to U gamma, then gamma is also path connected. Another observation is the Euler characteristic of the surface is actually sum of the Euler characteristic of this tree and the Euler characteristic of this graph, dual graph. The reason being, so if I just do the computation over here, just let me look at it. Okay, I've got some time. Okay, so if I look at uh, this thing, so our maximal tree, it will contain all the vertices and there will be edge between them. So this is the gamma t part, and for the Euler characteristic of the dual graph, I have a vertex for each of the face, and then I have another vertex for each of the one simplices which were not a part of the tree uh, T. So I've got this many. These are the number of zero simplices, and the number of edges is, I've got E minus V minus 1 edges. Actually, let me just uh, do it like this. So I know there's going to be 1, but let me just call it the number of edges in ET. I think in that way it helps me to do the calculation. Okay. So for each, okay, just come back over here. For each vertex, I have an edge over here. So the number of edges are E minus ET, and uh, are there any more edges over here? Sorry. So I've got one edge for each of them. If I plug in everything together, what do I get? I get uh, V. So if there's going to be a minus ET term, there's going to be minus ET plus F. So I'm missing some edges over here. Wait, what are the edges that I'm missing over here? Uh, I'm really sorry. I think I should have done that beforehand. So I've got a word zero simplex for each of the faces. So f plus e minus et, those are the number of faces. And for each of them, how many edges are there? So there is one edge. Oh, sorry. Yeah. There are two. Because like for each search, I'm getting two edges. Yeah. Now this makes sense. Yeah. Now if you just do the calculation, you will get e minus f plus. Yeah. Sorry about that. So these are the number of one simplices, and this is the Euler characteristic of gamma. Good enough. And now some quick observation. So if your graph G is connected, then the Euler characteristic is always less than equals to 1, and equality occurs if and only if G is a tree. So if it is a tree, then we know it is going to be 1, because then if there are V many vertices, then there are V minus 1 many edges. So the Euler characteristic is going to be 1. Okay. And if it's not a tree, then it contains a loop. And what we do is we remove an edge from that loop, then our graph still remains connected, but the Euler characteristic increases. And eventually we will reach a tree. So if you keep on doing that, what will happen is, so you have a graph G and you keep on removing edges until you get a tree from it, which I say like GT, and this will have Euler characteristic 1. So for any connected graph, this shows that the Euler characteristic is less than or equals to 1, and it is equal to 1 only when the graph is a tree. And an immediate corollary of this lemma is this thing. So since any surface can be triangulated, so the Euler characteristic is going to be the Euler characteristic of the triangulation, but then I can look at a maximal tree and I can look at its dual graph, and I know this result is going to be true. And T, this is a tree, and so its Euler characteristic is 1. And now this guy, I don't know what the Euler characteristic is, but this is a connected graph from our previous observation because U gamma was path connected. So this thing has to be less than or equals to 2. Great. We have done the hard part, and now let us finally come to doing surgeries. Okay. So start with a compact connected surface and a triangulation on it. So if your surface is sphere-like, then lemma will automatically tell you that it is homeomorphic to a sphere, and you are done. You don't have to do anything else. Otherwise, if it is not sphere-like, then you know there is a simple closed curve in the simplicial complex such that this guy is connected, right? So what you do is, since this guy has same homotopy type as this guy, you look at this guy. Okay, you look at the simplification complex, and then you cut out the neighborhood which is found by thickening your curve C. And once you remove the interior of this collar like neighborhood, it may happen that so this collar like neighborhood, it is either a cylinder or a Mobius strip. This is also something that we have already observed. So if it's a cylinder, then I know if after removing it, I will get two copies of S1. Or if it's a or if it's a Mobius strip, then I will get only one hole, and so I will get only one copy of S1. So let us look at this big diagram pictures. I think the pictures will give you a much better idea. So this is a picture of a torus, and what I've done is look at this curve. This curve, after I cut it, then our space still remains path connected. So I look at a collar-like neighborhood around it, which is the blue part in the shaded figure, and then I cut it. I get two copies of S1. So these are two disjoint copies of S1. And what I do is I cone them off. So I take another vertex and then I cone them off to get a new space. And surprisingly, this looks like a sphere, right? Mm, well, we will see. Like, this is not a surprising fact. This is eventually what is going to be true in most of the cases. So another example, when you have a non-orientable surface. So I have taken example of a real projective plane, like which is just a sphere with a Mobius strip attached. So again, if you are familiar with quotient topology, I think you know that this guy is just a sphere with a Mobius strip attached to it. So what I do is I look at the equatorial circle on the Mobius strip and I cut along that. Remember, I have told you that the equatorial circle does not disconnect the Mobius strip. So if I cut along that, I get another path connected space. But this time what I get is after removing the interior of like the blue shaded region over here, I get a sphere with a hole in it. So I have a sphere and I have a cylinder attached to it and which is empty at the top. What I do is I cap it off. Okay. I cone off the cylinder and once again looks like this is homeomorphic to S2. Great. So this is the idea behind doing surgeries. And like so the but how do we get back our original surface? So this is very easily done because when you are doing the cutting and pasting, what you do is you just remember how you had cut and how you, then what you will do is we'll just redo our stuff. So if you had cut along a non-oriented curve, what we'll do is when we redo the stuff, we will just attach a Mobius strip to it, which is what I've done over here. So if I've cut along a non-oriented curve, I will just attach a Mobius strip along the boundary circle, which I will mark beforehand. And if I had cut along a oriented curve, then I know I will get two copies of S1. Like in this case, I will get two copies of S1, and what I will do is I will just attach a handle to it and this will give me the surface which I had started with. So sort of this is the idea of desurgery. You do surgery, then you do desurgery to get back your surface. Now, why is doing surgeries helpful? Well, this diagram actually gives you the answer. So as you keep on doing surgeries, your Euler characteristic keeps on increasing. Okay, so just an example over here. So this is an arbitrary space X. And suppose I'm cutting along an oriented curve over here. So I cut along this guy and I get a new space X1 after coning of the cones. So what is the Euler characteristic of this guy? So this is going to be the Euler characteristic of the space X, which we had started with. And now I have to remove the part which comes from the Euler characteristic of NC, the collar-like neighborhood. So I remove that part and finally, I have to glue in the two cones part. So I have to attach the Euler characteristic of the cone 1 and the Euler characteristic of the cone 2. And what this guy is going to be is uh, so the Euler characteristic of x is just Euler characteristic of x. It stays whatever it is. And now the Euler characteristic of NC, if you look at the following triangulation on the cylinder. So this is our cylinder and I give it the following triangulation like this. Great. So if we compute the Euler characteristic for this triangulation, you will get that the Euler characteristic of the cylinder is 0. And in the case of Mobius strip also this triangulation works. So if you have a Mobius strip then also this triangulation will work. So this is going to be 0. And what is the Euler characteristic of the cone? I think which is again very simple. So the Euler characteristic of a cone is just like a disc, right? So what I can do is I can just take this kind of a surface. Uh, Sorry, I'm just being a bit too lazy over here. Yes, I will just be keep it like this. Okay. Sorry about this. Oh, sorry. Maybe just you can look at the disc like this, and then I'm looking at this triangulation. And if you compute the triangulation of this guy, you will get it is 1. So you will get 1 and a 1. So that means the Euler characteristic becomes 2. So it increases by 2. And in case of a non-oriented curve, you will get only one disc. So when you will remove that and attach a disc to it, you will get the Euler characteristic will increase by just 1. Now, proof of the main theorem. Well, with all that hard work that we have already done, the proof of the main theorem is very simple. Take any surface X and triangulate it. Now, if it is sphere-like, then we are done. So if it's sphere-like, we are done because in that case, X is homeomorphic to S2. If not, okay, next step. So if it's not, then there exists a polygonal closed, a polygonal simple closed curve C in K, and what you do is you do surgery along C, and in fact, and you keep on doing this with the new surface until and unless, so you keep on doing this until and unless the Euler characteristic of the resulting surface is 2, and in that case xn by lemma 1 again, this is going to be homomorphic to S2, and then what you do is you do all the necessary desurgeries. But what were the possible desurgeries? So basically, if you have done a surgery along an oriented curve, you have to attach a handle, so which are attaching handles and attaching Mobius strips. So our resulting surface, but then our resulting surface, which is X, which we obtain after doing all the D surgeries, is either some sigma G or X is Ng. Well, why? Because if you had done, say, if you had to do some surgeries along oriented and also along non-oriented curve, then from our earlier observation, we had shown that in presence of a Mobius strip, the attaching a handle is same as attaching two Mobius strips. So if that is the case, then also you can just make them fall into one of these classes, and that completes the proof of the main theorem. So this completes the proof of main theorem. So how much time do I have? Well, I have barely any time, but I want to quickly give a proof of lemma 1 that will sort of complete this whole argument. So a proof of lemma 1. So just before going to the proof of lemma 1, so this is what we had actually done in these two examples. So I started with a torus. I had cut along an oriented curve. I got a space like this, and then I did a surgery to get a space which is homeomorphic to S2. Now to get back from S2 to this guy, I have to do some desurgeries. And what is the desurgery? I have to just attach a handle along this guy. So I will remove the disc, and when I will attach a handle like this, I will end up back with the torus. And same thing with the Mobius strip attached to the sphere again. So in that case, I will remove this cap and I will attach a Mobius strip over there to get back over here. Desurgery. Okay. So that was the idea behind the proof. So you keep on doing surgeries until the Euler characteristic reaches 2. Now you know that space is, it looks like a sphere, and you do the desurgeries, which is just attaching handles and attaching Mobius strips. Then your eventual surface is sigma g or ng. And a proof of lemma 1, I know I'm run out of time, but I will just take 5 more minutes. I hope that's fine. Is it? Okay. I will just finish it off. I hope there isn't a problem. If there is something, just let me know. Okay. So proof of A to B. Say your Euler characteristic was 2. Just on so take a maximal tree T in S and gamma be its dual graph. Then from our observation, we know that gamma t plus the Euler characteristic of the t and gamma is same as the Euler characteristic of your surface S, which is 2. But tree was this was a tree, so this is 1, which will imply that the Euler characteristic of the graph gamma is also 1. That will imply that gamma is a tree from lemma 2. But your triangulation K, if you remember, it was union of NT and U gamma along the boundary. That what so this guy is homeomorphic to D2 and this guy is also homeomorphic to D2 and we are attaching them along the boundary which is S1. So K is actually homeomorphic to S2 and that proves A to B. Well, B to C is something that we have already done by taking the trivial triangulation, by taking a tetrahedron kind of triangulation on the sphere. So this is already done. For the last part, C to A, once again take a maximal tree, maximal tree T and its dual graph. What I will show is the dual graph is also a tree. Okay. And how do we do that? If gamma is not a tree, then we know it will contain a loop. It contains a loop which consists of one simplices. But then, so let us call that by let it be C. Then K minus C is disconnected, right? The reason being that uh, uh, our space was sphere-like. So if K minus C is disconnected and each of the component contains some vertex, right? Because those are each of the components non-empty. But then this gives us a disconnection of T because like if this is some U union V, this contains these are disjoint U and V are disjoint over here with disjoint neighborhoods, disjoint open, and each of them contains some vertex of the tree and each of them contains some vertex of tree and since T was disjoint from C like this gives us a disconnection of the graph tree and this is a contradiction because contradiction because T is connected. I had to rush through the last part. I wanted to keep this part a bit more save some more time for the last part but it didn't happen like that. So any questions? Then otherwise I will end it over here.
Uh, Excuse me.
Yeah.
You said gamma and U gamma were some sort of homotopically related. Can you elaborate on that? What exactly does it mean?
Sorry, I didn't get your question. What exactly do you mean?
You said gamma and U gamma. are
Yeah.
related as type of homotopy or something.
Oh, so what I was saying over here, so uh, where did I define U gamma and gamma? I think over here. So yeah, what I was saying is, so remember our space L was a collection of some subsimplices of dimension 1. Okay, what I want to do is I want to create a neighborhood along them, along this guy over here, which is which has the same homotopy type as L. So say this is my N. This is just an arbitrary neighborhood N. Around it, what I so our goal is to get N such that N is homotopic to L. If you know what homotopy is, uh, basically what we want is, so if you don't know about homotopy, what we want is, so doing this kind of a deformation, if you if you go back from your neighborhood to your curved line, this is sort of, what to say, like a uh, this is more or less gives you the same nature as the line L. So this neighborhood up almost has the same nature as the line L. It is not homeomorphic, but it is homotopic. So I don't think I can do it better without just going into homotopy. But if you know about homotopy, this is what I mean. And same with the uh, neighborhood UT. So I think I defined UT over here. So yeah, so I want a neighborhood around this guy, which is homotopic to the graph gamma. So U gamma should be homotopic. So if I call this U, ah, if I call this U, I want U to be homotopic to gamma. And the bicentric subdivision was done solely with the purpose to get such neighborhoods U gamma and NT so that they are homotopic to the one-dimensional subsimplices gamma and T. I hope that clears that out.
Okay. Yeah. And just to be clear, the act of performing surgeries and desurgeries are not
Yeah.
homeomorphic, right?
I didn't get the question. So what do you mean?
I saying that the act of performing the surgeries and desurgeries are not homeomorphic,
Oh,
right?
yeah, yeah, of course. This is not at all homeomorphic to this guy, and
Yeah.
neither is this thing. So,
Yeah.
but when I do the desurgery, I get back our original space. So that is
Okay.
what.
So
So this is also not a homeomorphism. But what when I do all this process together, so basically this is not a map, right? Doing surgery is not giving a map. What you are doing is changing your space completely. So
yeah.
like the arrow is not like you are giving a map. You are completely changing your space. What I'm telling is, like, after doing a certain number of surgeries, if you keep doing the necessary desurgeries, you will get back your space.
Okay.
Yeah. Okay. So
If I remember
yeah.
correctly, there's a formulation of Euler characteristic in the form of genuses as well. So
Yeah. Yeah.
what
Yeah.
I'm
Yeah. There.
saying here is like when you perform a surgery, you just reduce the genus by two.
Exactly. When you are doing a surgery along an oriented curve, you are reducing the genus by 2. And when you are doing a surgery along a non-oriented curve, you are reducing the genus by 1.
Yeah.
I'm very sorry. In either case, sorry, I said something wrong over there. In either case, actually, what we are doing is we are the genus. So if you know about what genus is, in each step of the surgery, we are actually reducing the genus by one, not by two, or not by two. Like in either case, we are reducing the genus by one. If you know what genus is.
Okay.
Okay. So
Okay, if no one has any more questions, then maybe we could end the talk here. Thank you, Shona.
yeah,
And
thanks a lot.
there's a poster session from 3:30 onwards, so you could join there from, I guess, 3:20, 25. See you there.
Oh.